Lecture 1, Inventory Control with Known Demand, Part 6. In this part, we will have the all units quantity discount and also incremental quantity discount models. So let's at first the all units quantity discount model. So in order to explain this model, we do this by an example here. So here when we have an example, the annual demand is 600 units per year. Holding cost interest rate is 20%. Fixed cost of listing an order here is $8. And as you see here, the purchase price, I mean the unit purchase price is dependent to the quantity. If the order quantity is between 0 to 500, then the unit price is just 30 cents. If quantity lies in between 500 and 1,000 units, then price decreases to 29 cents. There will be 1 cent as discount. And if quantity is greater than 1,000, then price could be 28 cents. Okay, so let's see, by having the situation that the unit purchase price is dependent to the order quantity, then what could be the optimal quantity for ordering? Okay. So to solve this problem at the first step, we consider the unit purchase prices separately, and then we'll solve separately for EOQ to see if the EOQ, I mean the optimal quantity of ordering, lies in the corresponding interval for that unit purchase price or not. So here Q0 is for the first interval, Q between 0 to 500. Q1 is the second interval, Q between 500 and 1,000, and Q2 is for the third interval, Q greater than or equal to 1,000. So as see here, by having the unit purchase price of 30 cents, 29 cents, and 28 cents, we have solved the EOQ, and we do have the values here. So as you see here, just the first one, I mean EOQ for the first interval, I mean for 30 cents, lies in that corresponding interval. But the next two are not feasible somehow, because here we are assuming 29 cents, but the order quantity is 406. But in order to have 29 cents, the order should be greater than 500, right? So it's impossible, it's infeasible. And also for the third one, by having 28 cents, the quantity should be greater than or equal to 1,000, but here it's not. So it's again, it's impossible. So the only one that we can we can go with that. I mean, it's possible, it's feasible, is the first one, because the quantity lies between 0 to 500. So what should we do by having this situation here? So in this situation, we can say the average total cost for our inventory system for every quantity interval with their corresponding unit purchase price would be the shaded actually curves, as you see here. Yeah, I mean between 0 to 500, this is our curve for average cost, and the minimum is somewhere around here, which is regarding to 400, right? 400 units. And then we go for the next interval over 500. Our average cost would be this curve, and then again over 1,000 it will be this one. So here for the first interval between 0 to 500, we do have a feasible solution, which is 400 units for EOQ. But for the next two intervals, I mean between 500 to 1,000 and over 1,000, we don't have a feasible solution. So here the feasible solution would be 500 for the second interval and 1,000 for the third interval. I mean breakpoints. The breakpoints would be considered as the ordering quantity. So, and then we will calculate the total average inventory cost for these three options. One option is the EOQ for the first one, and for the next two intervals, the lower limit, I mean the lower breakpoint here, 500 and 1,000 would be our options for ordering, and we'll see which one actually has a lower average inventory cost, and that will be our optimal ordering quantity. Okay. So here we do have three options. J0 refers to interval between 0 to 500. So for this interval, we do have EOQ as 400 units. J equals 1 will be the second interval, Q between 500 to 1,000. So for this, the Q should be 500. And for the third interval, J equals 2, Q over 1,000. And for this, Q will be 1,000. Okay, so in order to calculate the average annual cost, we do have this equation, right? Lambda times C. Since here unit purchase price is different in each case, so we need to consider the purchase cost as well. So lambda times CJ plus lambda times K over Q for the ordering cost, and ICJ times Q over 2 for the average inventory holding cost. So if we substitute the Q for each interval, for the first one is 400, the second one is 500, and the third one is 1,000, right? And then calculate the average annual cost as you see here. So for 400, we do have this number for the average annual cost, $204. For 500, we do have $198.10, and for 1,000 we do have $200.8. So as you see here, the minimum is for 500. So because of that, the QS star becomes 500. Okay. So let's summarize the steps to solve the all units quantity discount model. The first step, we determine the largest realizable EOQ value. So we start from the lowest price, lowest purchase price, and then continue with the next higher price until the first EOQ falls in the correct interval of Q. Okay. And then in the step 2, we should compare the value of the average annual cost at the largest realizable EOQ, which we obtain in the first step, and at all the price break points, the lower limits of the next intervals, price break points that are greater than the largest realizable EOQ. Okay? So the optimal Q would be the point which the average annual cost is minimal. Okay. So let's consider the incremental quantity discount model. So here, if Q lies between 0 to 500, the price would be 30 cents. So 0.3 times Q would be the total purchase price for each order. Okay. So, but if Q is between 500 and 1,000, the first 500 units will be 30 cents. So 0.3 times 500 becomes 150 here, and the rest will be on $0.29. So in total, the purchase cost for the order becomes 5 plus 0.29 times Q. Okay. And if Q is over 1,000, we do have this term. So here we do have the total purchase cost for each order. Okay. So if we divide this CQ term, the total purchase price, by its quantity Q, then we can say somehow we are calculating the average unit purchase price, right? So yeah, so CQ divided by Q for the first interval, it becomes 30 cents. For the second interval, we do have two purchase prices, 30 cents for first 500 and 29 cents for the rest over 500. So in average, the unit purchase price becomes 0.29 plus 5 over Q. Okay, and for Q over 1,000, we do have three unit purchase prices, and the average here becomes 0.28 plus 15 over Q. Okay, so here the GQ, the average annual cost, if you remember, in general was lambda times C plus K lambda over Q, and plus I times C will be H, and then times Q over 2 for the average holding cost, right? So here for the C, we do have this term, CQ over Q, which is the average unit purchase price, right? And again, for C here, we do have this term. So as you see, by having that average unit purchase price, we can write the average annual cost function for every interval. Okay, so yeah, by having this average annual cost function, we will replace CQ over Q for each interval. Then we will have a unique average annual cost function for each interval, and then we will solve that for Q. So how we need to take the first derivative of the GQ with respect to Q and then set it to be 0, and then by solving that equation for Q, we can obtain the quantity, the order quantity, or Q. Okay, so for the first one, since the price, we do have just one price, it's C0, so the EOQ becomes 400. But for the second interval, we do have a term for average unit purchase price. Okay, so if we do that, which is 0.29 plus 5 over Q. So if we replace the CQ over Q by this, and then having other parameters here, so we'll have this function. And now if you take the first derivative of this function with respect to Q and then set it to be 0, and then solve that equation for Q, you will obtain this quantity 519. Okay, and we do the same for the third interval Q2, and the value becomes 702. So as you see here, for the third interval, Q should be over 1,000, but as you see here, it's not, so it's infeasible, right? So just the Q0 and Q1 are feasible here, so we just do have two feasible solutions. So we calculate their associated average annual cost to see which one is minimum, and that one would be our optimal ordering quantity. Okay, so the G0, the annual average cost for Q0 is 204, and for Q1 is 204.55. So yeah, a little difference between these two, but yeah, by choosing the minimum, 204 is minimum, so the optimal order lot size becomes 400 units. Okay, so to summarize the procedure for solving the incremental discount model, at first we obtain an algebraic expression for each price interval, CQ, and then by dividing that CQ by Q, we will obtain the average unit purchase price, and then we will substitute C cubed over Q in the average annual cost for C. So we do have a unique GQ for each price interval, and then in order to obtain the EOQ for each price interval, we need to take the first derivative of that price function with respect to Q and then set it to be 0 and then solve that equation for Q. So by doing that, you obtain EOQ for each price interval. So we'll obtain which EOQs are realizable. They are feasible. They fall in the corresponding interval of Q, and then by having the feasible ones, we pick the one with the lowest average annual cost as our optimal EOQ. Okay, Thank you.